In recent years, scientists have used many advanced technologies that help us better understand the Earth's surface. Satellites, ships, and research facilities receive and send all kinds of information used by researchers worldwide. Information that shows how enormously complex our planet is. And it's huge. The Earth's surface area covers almost 197 million square miles. That's more than 509 million square kilometers. Fortunately, there are a number of devices that help us quickly understand the many complexities of our Earth. One that's been around a long time is the globe. Globes, which are small models of our planet, show us where water and land are located. They also show their proper shapes, but in a much smaller version, of course. Most globes tell us how much smaller they are on their scale, which is found in its legend. Scales are stated as a ratio, here rounded off, 1 to 42 million. The first number of a ratio, generally a 1, represents the real thing. A colon is the ratio sign. The second number, we'll call it n for now, tells you how many of the model are needed to equal the real thing. If the real thing and its model have a 1-to-1 ratio, for example, it takes only one of the model to equal the real thing. But if the ratio is 1-to-4, it takes 4 of the model to equal the real thing. Stated as a ratio, 1-to-4. Now, returning to our globe, you'll remember that its scale is roughly 1 to 42 million. That's true of many globes because in the Earth's diameter, there are about 42 million feet. In other words, this globe has been scaled down to 1 foot, or 12 inches, from the 42 million feet, that's 67.6 million kilometers, found in the real world. If you're looking for a place on a globe, the main directions, north, east, south, and west, can be a big help. Of course, you have to understand some basics before you can use those directions. First, south is always pointed toward the South Pole on globes, and predictably, north is always pointed toward the North Pole. When the globe is positioned so that the North Pole is located at the top, which is generally the case, north is up, south is down, west is to the left, and east is to the right. North, west, south, and east are known as the cardinal directions. Directions can be important when you need to find a place on a globe. If, for example, you have to find Copenhagen, Denmark, and you know where Tripoli, Libya is, and you've been told that Copenhagen is north of Tripoli, you would merely move your finger up, northward, toward the North Pole, until it runs into Copenhagen. There it is. But what if you don't know where Tripoli is located? Many people don't. Nevertheless, you can find it. Or Copenhagen, or any other place for that matter. Because a series of lines that runs east and west, and another that runs north and south, a grid, is printed on globes to help us find particular places and measure distances. We'll explain how in a few minutes, but first, a definition. The lines that run east and west are called parallels of latitude. In the real world, these imaginary lines are always the same distance from one another, about 70 miles, or roughly 113 kilometers. If you look down from the North Pole, you can see that parallels of latitude form circles, which are measured with a unit called the degree. Degrees are symbolized by a small circle. The distance between each latitude is subdivided into units called the minute. There are 60 minute lines between each line of latitude. Minute lines are symbolized by an apostrophe. The basic reference latitude, the equator, lies halfway between the North and South poles, at precisely 0 degrees, 0 minutes. The equator divides the globe into its northern and southern hemispheres. Our word hemisphere comes from a Greek word meaning half a sphere or half a globe. For every degree of latitude in the northern hemisphere, there's a corresponding degree in the southern hemisphere. To distinguish between them, we say a place is located at so many degrees north or so many degrees south. For example, we could say that the northern edge of Cuba lies at 23 degrees 30 minutes northern latitude, and that Sao Paulo, Brazil lies at 23 degrees 30 minutes or 23½ degrees southern latitude. By the way, 23½ degrees southern latitude is called the Tropic of Capricorn, and its corresponding latitude in the northern hemisphere is known as the Tropic of Cancer. The area between these two latitudes, often called the tropics, has a tropical climate, warm and often humid all year long. Two other lines of latitude, the Antarctic Circle at about 66½ degrees southern latitude, and the Arctic Circle at 66½ degrees northern latitude, also help identify climate. The areas within these circles are generally cold throughout the year. The areas between the tropics and the Arctic Circle and the Antarctic Circle, those in the so-called middle latitudes, generally have more seasonal weather, with a summer, fall, winter, and spring each year. So far, we've discussed the first part of the grid system found on globes, parallels of latitude. Now let's take a look at the second, lines of longitude, also called meridians. As you can see, they run north and south, and unlike lines of latitude, they don't lie parallel to each other. They bulge out at the equator, then get closer together until they finally intersect at the South Pole and North Pole. By the way, meridians also form rings around a globe, but these rings run north and south, unlike the rings formed by parallels of latitude, which, as you recall, run west and east. The lines made by meridians are measured in the same way as lines of latitude, in degrees and minutes. The standard reference meridian, located at 0 degrees, 0 minutes, is usually called the prime meridian. Because it runs through Greenwich, a town just outside London in the United Kingdom, it's sometimes referred to as the Greenwich Line. When other meridians are drawn to the east of the prime meridian, we identify them by saying 15 degrees east, 30 degrees east, 45 degrees east, and so on. When they're located to the west, we say 15 degrees west, 30 degrees west, 45 degrees west, and, well, you see how it works. Now, let's see how that grid composed of latitude and longitude lines can help you find places on a globe. Let's say you're looking for Saudi Arabia, which is found at 45 degrees eastern longitude and 25 degrees northern latitude. Look along the equator until you find 45 degrees east. Find 25 degrees northern latitude on the rim holder or on the globe itself. Move your fingers together, and where the two meet, at 45 degrees eastern longitude and 25 degrees northern latitude, you'll find Saudi Arabia. Up to this point, we've discussed globes. Now it's time to turn our attention to maps, a second device that helps us quickly understand the many complexities of our Earth's surface. Of course, people use maps all the time. A repair person may access a map on a laptop to find the fastest way to get to his customer. Scientists use maps for any number of reasons. Many of us look at weather maps to find out what we should wear to school on a particular day. Obviously, maps are very useful and have been for a long time. In 16th century Europe, a map maker or cartographer named Gerardus Mercator devised a way to make a map that showed directions more accurately than ever before. We can reenact what Mercator did by wrapping a plastic tube around a transparent globe. Mercator put a candle inside his globe, but being more modern, we'll use a light bulb. When lit, the shadows cast by the lines on the globe are projected onto the plastic tube. Now, if you trace the shadow lines carefully, you get a map. Mercator projection maps, as they're called, give a true picture of directions. But places such as Greenland and Antarctica are distorted on Mercator maps, which stretch out shapes far to the north and far to the south. If a person wanted to make a map with less distortion, he or she could use what's called a Lambert's or conic projection. These maps can be made by using a cone that touches a smaller portion of the globe than does the tube that produces a Mercator projection. You'll see that while you're tracing, the projected shadows have practically no distortion. That's because the shadows are closer to the globe. So distances, shapes, and directions are more accurate on Lambert projection maps than on those based on Mercator projections. But Lambert projection maps show smaller areas. Not all large-scale maps are made by the projection method. Some, such as this one, show that different methods can be used. In fact, you can use your own method. If you paint an orange so that it looks like the Earth, and then cut its skin into equal slices, peel off those slices, and then lay them out flat, you have still another kind of map that represents the Earth's surface. During this part of the program, we've looked at the various ways that information on a globe can be transferred onto a flat surface to produce a map. And we've talked about some major map projections. Now we're going to turn our attention to some maps that convey specific kinds of information, often called special purpose maps. The graphic relief map, or variations of it, is commonly seen in geography classes. Sometimes called a physical relief map, its different colors show how high or low the land is in relation to sea level. Most graphic relief maps use browns or dark oranges to depict mountains. Yellows and beiges are used to indicate hills and uplands. Various shades of blue generally show water. Light blues normally show shallow water, often near a coastline. Greens usually mean lowland areas. Sometimes colors are used to show information other than the height of land or depth of water. On this special purpose map, for example, colors show population density. Each color indicates how many people live within a square mile. Small colored squares explain what each color means. The squares are found on a portion of the map known as the key or legend. Now look at this land use map. Using the color squares in the legend, can you tell whether there would be much gathering activity near Sydney, Australia? No, of course not. As the map shows, Sydney is located in an industrial and a farming area, not a region noted for its gathering activity. Students often refer to political maps when studying geography. Political maps show boundaries between states or provinces and between countries. Often, broken lines with one dot between them are used to show state or provincial boundaries. Sometimes, a transparent line is overlaid on them. Broken lines with two dots between them often depict the border between countries. Finding places on maps is somewhat similar to finding them on globes. In atlases, which are books of maps, parallels of latitude numbers are found at the right and left edges of the map, and longitude or meridian numbers are found at the bottom and top. If you knew that Winnipeg, Canada was located at about 50 degrees northern latitude and at about 97 degrees western longitude, you could easily find it on a map. People also can find a lot of very useful geographical information online. Suppose, for instance, you and your family were planning a vacation in San Francisco, California, and wanted to see Fisherman's Wharf, a popular tourist attraction there. Well, you could obtain its location online, making it easy to find when you arrive in that Northern California city. By the way, letters such as A, B, and C, and numbers such as 12 and 13 are often placed on the edges of small-scale maps to help people find specific locations. For example, the corner of Judah Street and Sunset Boulevard is located close to where B and 12 intersect. Expressway users also can get up-to-the-minute traffic report maps online so they can avoid traffic jams. Moreover, travelers can find maps that give the best route when going from one city to another. And of course, maps on paper are useful because they can be carried wherever you go. In that respect, they're much more useful than globes. Up to this point, we've discussed globes and maps. Now we're going to talk about graphs, the third category of devices that help us quickly understand geographic information. Before you can use a graph, you need to look at its title. Here, the title tells us the graph shows the world's population during a 100-year period, from 1925 to what it's projected to be in 2025. It also states that the numbers given will be in billions. Now that you know what the graph is about generally, world population, you can get down to specifics by looking at the information near the vertical axis on the left side and along the horizontal axis at the bottom. The vertical axis shows the number of people or population, in this instance in billions, just as the title states. The data on the horizontal axis gives the basis of the comparison, the years in which the population numbers have been tabulated or projected. Because the data are shown on vertical bars, those that are drawn up and down, this kind of graph is called, quite logically, a vertical bar graph. You can find specific information on these graphs easily. If, for instance, you wanted to know how many people there were on Earth in the year 2000, you'd first locate the top of the bar that's labeled 2000. Then look to the left on the vertical axis where the numerical data are listed. As you can see, there were a little more than 6 billion people in the world in that year. Remember, the numbers shown are in billions. Sometimes the bars in bar graphs are divided into sections to give more detailed information. Here, you can see that the continents are now divided into major countries. Given this more detailed information, you can make some educated guesses about the countries. The United States, for instance, consumes far more energy than any other nation. Therefore, a good educated guess is that the United States has a much more extensive transportation system. because large numbers of planes, trains, ships, buses, and cars require energy to move. So far, in this section of the program, we've discussed vertical bar graphs. There are also horizontal bar graphs. The upcoming example, as you can see, will compare steel output in the leading steel-producing countries. On horizontal bar graphs, numerical data almost always lie along the horizontal axis, and the things to be compared along the vertical axis. Occasionally, the bars are segmented to show two or more classifications of the data. Here, it's 4 kinds of steel, as seen in the key: carbon, alloy, stainless, and tool. Of the 4 leading steel-producing countries, which produces the most stainless steel? Right. You can see at a glance that it's Japan. How much more carbon steel is made in China than in Russia? Well, since there are about 100 million metric tons made in China and about 40 million metric tons in Russia, the difference, 60 million metric tons, is the answer. The next kind of graph we'll look at is the line graph. It's normally used to show trends or movement over time. That can be very important when studying geography. The worldwide growth of desert lands is an example. As you can see, the percentage of world lands that are deserts are shown on the vertical axis, and the years on the horizontal axis. The graph line shows that during the past 50 years, desert lands have grown from 18.5% of all the world's lands to now almost 20%. Scientists use this data to predict future trends and to develop strategies to solve problems. For instance, new tilling techniques were developed to reverse the growth of desert lands after scientists recognized the trend. Multiple line graphs, those with more than one line, are used to compare trends. This multiple line graph, for example, shows population growth trends in developing regions of the world as compared to population trends in already developed regions. As you can see, the data is projected all the way to 2050. Graphs such as this one can be very helpful to diplomats and other officials who need to plan for the future. In developing countries, such as those in Latin America or in Africa and Asia, officials need to plan so that there will be enough jobs, housing, and food for the billions of people who will be born in the years to come. So far in our discussion of graphs, we've covered the bar and line varieties. Now we're going to turn our attention to circular graphs, sometimes called pie charts, because they're divided into wedges, much like a pie. The wedges show how the total amount is divided up. Let's say that you're studying Brazil, and you need to find out how most of the people in that South American country earn their living. A circular chart can quickly tell you. Well over half of all Brazilian workers earn their livings in service jobs or in agriculture. Which occupational area has the smallest number of workers in Brazil? Obviously, transportation and communication. Pictographs are the last kind of visual device we'll discuss. Sometimes called picture graphs, they have small drawings or symbols that represent specific data. All pictographs have a key that explains what those symbols mean. Here, 1 wheat stalk represents 10 million metric tons of wheat. From this graph, you can tell at a glance that China produces the most wheat of the countries and region compared to it, the European Union, the United States, and India. If you quickly count the stalks, you can see that it produces 110 million metric tons of that grain. In short then, charts, maps, and globes show data in a way that can help us understand many different aspects of geography quickly and efficiently. But before we can use them, we need to understand some basics. Scale, parallels of latitude, lines of longitude or meridians, map projections, directions, the meaning of colors, and what's on a graph's vertical and horizontal axes. Globes, maps, and graphs. They are very useful tools we can all use.